Now we will begin our explanation related to Thermistor Workshop Basics, Part 1, NTC Thermistors and Temperature Sensor Circuits. In recent years, as sensors become more functional and more densely mounted, demand for temperature sensor circuits has grown. In NTC thermistors, their resistance value decreases as the temperature rises. For this reason, they are often used in products for temperature sensing. Here we present an example of a temperature sensor circuit using a thermistor. One way to ensure the proper operation of a product is to define a response triggered by temperature increases, such as the sounding of an alarm, a fan turning on, or the product discontinuing operation. Now let's take a look at the SMD type components used in temperature sensor circuits. These consist mainly of 4 categories: thermistors, analog IC temperature sensors, digital temperature sensors, and IC integrated temperature sensors. Thermistors, analog IC temperature sensors, and digital temperature sensors are used to measure the temperature of circuit boards, and IC integrated temperature sensors are used to measure the heat generated by ICs. Comparing the 3 types of components used to measure the temperature of circuit boards, thermistors offer features such as smaller size, lower costs, and excellent supply stability compared to analog IC temperature sensors or digital temperature sensors. Using a thermistor or an analog IC temperature sensor requires an ADC, but microcontrollers and PMICs provide plentiful AD ports for connecting to an ADC via a multiplexer, so we recommend simply using a free AD port. Digital IC temperature sensors provide high temperature accuracy if you spend sufficient money. They can also produce digital output via an interface such as I2C, so no ADC is needed. Now let's compare thermistors and digital IC temperature sensors in some more detail with regard to 3 items. First, we will compare the mounting area or footprint. Building a temperature sensor circuit using a thermistor requires 3 types of components: a thermistor, a resistor, and a bypass capacitor. On the other hand, when using a digital IC temperature sensor, 3 or 4 pull-up resistors and 1 bypass capacitor are needed in addition to the digital IC temperature sensor for a total of 5 or 6 components. This means if we compare components of the generally used size, using a thermistor will result in a footprint less than half the size of that when using a digital IC temperature sensor. Second, let's compare the cost of components. If we compare circuits with a temperature range of -40 degrees Celsius to 125 degrees Celsius and a temperature accuracy of around plus or minus 3 degrees Celsius, the circuit using a thermistor ends up costing approximately 1/10 what the circuit using a digital IC temperature sensor costs. Third, we will compare the design examination process. When it comes to determining factors such as what is the temperature we would like to sense, where should the temperature sensor be placed, what are the temperature limits, and what level of temperature accuracy is necessary, and what temperature sensor interface will we use, there is no difference between thermistors and digital IC temperature sensors. Nevertheless, the difference becomes apparent when it comes to component selection. In the case of digital IC temperature sensors, temperature accuracy is listed as a specification on the datasheet, and this makes it easy to select the appropriate product number. On the other hand, there is no temperature accuracy specification listed on the datasheet of a thermistor. This means that the designer has to calculate the temperature accuracy. In addition, it is necessary to calculate the relationship between temperature and voltage, which is determined by the selected circuit, the thermistor, the R1 resistor, and the ADC specifications, and write the result to the IC incorporating the ADC. However, if you use the SimSurfing operation simulator on Murata Manufacturing's website, making these calculations is a simple task. What's more, once you design a temperature sensor circuit using a thermistor, you can continue to use the same design moving forward. Continuous reuse of thermistor circuit designs can provide a significant cost advantage. Now we will describe a temperature sensor circuit using a thermistor. This is what a typical circuit example looks like. The thermistor and resistor R1 are arranged in series and connected to voltage and a ground, and an ADC is connected between the thermistor and resistor R1. A voltage dividing circuit is formed between the thermistor and R1, and converting the resistance value to a voltage value enables the ADC on the IC to recognize the thermistor's resistance value, which varies with the temperature as a voltage. The voltage applied to the ADC is represented by this expression. Now we will explain the expression using an example. Let's assume that resistor R1 has a fixed resistance value of 10 kΩ and that the thermistor we are using has a resistance value of 10 kΩ when the temperature is 25 degrees Celsius. When a voltage of 3V is applied to R1 and the thermistor, the resistance values of R1 and the thermistor, which are connected in series, are the same, so the voltage applied individually to the resistor and to thermistor is 1.5 volt. This means that a voltage of 1.5 volt is applied to the ADC. Next, let's consider what happens when the temperature rises to 45 degrees Celsius. The thermistor's resistance value is now about 5 kΩ. The resistance ratio between resistor R1 and the thermistor is now 2:1, so the voltage applied to resistor R1 is 2V and that applied to the thermistor is 1V, meaning that a voltage of 1V is applied to the ADC. This graph shows the relationship between temperature and voltage converted from resistance. Note that the conclusions we can easily draw from this graph are described in Part 3, Design Support in SimSurfing. In Thermistor Workshop Basics, Part 1, NTC Thermistors and Temperature Sensor Circuits, we covered how to design a temperature sensor circuit that comprises only 3 components and an ADC. And we showed how easy it is to create such a circuit by inputting the ADC data showing the relationship between temperature and voltage into the IC. Thank you for your attention.